Hey there, chemists. Hopefully you had a chance to watch that short clip that I call Pretty Chemistry. The actual video of that, which I got from YouTube, is about 1 minute long, and I could just watch it. It's like a lava lamp. I don't know, I just find it very relaxing. So we're going to be talking about what's going on in that weird situation, because you got clear liquid makes yellow. I mean, everybody knows that from kindergarten, right? Clear plus clear makes yellow. No, I don't think so. So there's a little bit more going on. There's some chemistry going on. I'd encourage you to have your solubility rule chart handy, or one from the book, or just because we're going to be talking about solubility. Believe it or not, you actually have all the information in order to solve, to explain what's happening in there. Well, not quite all. Be nice maybe to know what those two solutions that we were mixing were. So in the dropper we had potassium iodide, and in the test tube lead 2 nitrate. So maybe take a second, pause the video, and write the chemical formulas for these. It would be good practice. We'll also be having to look at their formulas and dealing with them in just a sec. So you might recognize these as ionic compounds. So these are 2 different salts, 2 aqueous salts. So as we've discussed, so we're going to start with our dropper and what's going on in our dropper. So in order to make that aqueous potassium iodide, we needed to take solid potassium iodide and dissolve it in water. And when it dissolves in water, those ions dissociate from each other. The polar water pulls the ions apart and they spread throughout the solution. So let's then think about what that looks like. What's the dissociation equation for when potassium iodide dissolves in water? So again, I'd encourage you to pause and to practice. So the dissociation equation looks like this. Our potassium ion dissociates from our iodide ion, and we include those charges, and now they're dissolved in water. So let's do the same thing for our test tube. We have lead 2 nitrate. Remember that 2, that Roman numeral 2, does not refer to the subscript of the lead. It refers to the charge of that metal ion. So the lead 2+. So that's how I knew I needed 2 nitrates, because I know my polyatomic ions because I study them every day with flashcards. So pause the video and write the dissociation equation for when lead 2 nitrate dissolves in water. The dissociation equation should look something like this, where we have the ions, the ionic charges identified. We've separated them. We've moved this 2 in the front. These nitrates are not together in a crystal lattice structure anymore, but there are 2 for every 1 lead. So it should look like that. So hopefully you did a great job there. So we had these 2 aqueous solutions, clear aqueous solutions dissolved in water. And when we put them together, we're essentially mixing up all of these ions again, now with each other. So let's kind of think about what happens when we do that. So they're going to come in contact with each other, right? Because the kinetic energy of the particles, we know all matter is in motion at the particle level. So they're going to be moving around. I kind of think of it as mixing these 2 big dance parties, right? So what's going to happen when a potassium ion bumps into a lead ion? Well, they're going to repel each other, right? Because like charges repel, and opposite charges attract. So if the lead and the potassium come in contact, they're going to repel each other and go back into solution. What about when the potassium comes in contact with the nitrate? There's going to be an attraction there, right? Because the oppositely charged particles are going to attract. But here's the question: what's going to happen next? Are they going to stay together to create a solid, or are they going to come back apart? Well, as you guys you don't even need a solubility rules chart to check. You know that both of these are always soluble. They're always soluble ions. So when potassium and nitrate come together, they get pulled back apart by the water. So they might be together for a second, but then their attraction to water is pretty great too, and they get pulled back into that glorious dance party that is an aqueous salt solution. But what about our lead and our iodine? We can see that they're oppositely charged, so there's going to be an attraction between them when they come together. when they come together, is that attraction going to get pulled apart again by water? Well, hopefully you have your solubility rules chart out, because mine is very tiny on this screen. But if you look, I find iodide right here. So the negatively charged iodine atom, call it iodide, right here. And I can see that it's usually soluble, like we saw in this case. But what is one of the exceptions? There, lead 2+ is one of the exceptions, which means that lead iodide, when they come together, they form an insoluble salt, meaning something that won't dissolve in water anymore. So and then we're going to get that whole crystal lattice structure is going to get built. So I said I kind of think of this like a dance party. So this is how I like to explain it in terms of that dance party. So this is me, and I'm going to the dance party, and this is Justin Bieber, because I'd be willing to dance with Justin Bieber, especially if he cut his hair and only sang sorry and really didn't talk otherwise. You know, I'd be willing to dance with him, and I'd be willing to dance with the other people there, like, you know, the water, right? So dance with them, dance with Justin Bieber, that's fine. You know, this is Kate from The Office, and I hate her because she's wearing the same dress as me. So if we get near each other, we do not dance. We push each other away and move on. And this here, this lead 2+ ion, this lead ion, is Liam Neeson, right? And if I am at a party dancing with water and Justin Bieber and ignoring Kate because I hate her, and Liam Neeson shows up, am I going to want to dance with anyone else anymore? No. No, I am not, because Liam Neeson manages to be hot even in the Lego movie, even as a Lego. I don't know how that's possible. So, all kidding aside, the analogy kind of works, because I'm talking about, like, I'm just so attracted to Liam Neeson that I wouldn't be willing to dance anymore with anyone else, and I'm leaving the party. And we have to stop it there to maintain our PG rating. But the truth is that these ions really are electrostatically so much more attracted to each other than they are to the other ions or the water, that they come together and they form the salt, the lead iodide, which happens to be a yellow solid, giving us that really cool color that we saw when the clear plus clear makes yellow. So what we're looking at is called a precipitation reaction, or as I like to call them, a Liam Neeson reaction. So in our precipitation reaction, here's our definition. It's a reaction in which an insoluble product, so remember, insoluble means won't dissolve or can't dissolve, an insoluble product is formed when we mixed two solutions. So we had two aqueous solutions, two salts that would dissolve in water. So therefore we made that aqueous solution. When we mix them, we create something by the mixing of those ions that can't dissolve in water. And a biological example of this is the formation of kidney stones. Different ions from your blood and your diet come together, and they can make insoluble products, which can then lead to very painful kidney stones. The insoluble product that we create, which was in this case was our lead iodide, is called the precipitate. And we call it that because it's like it precipitates, it rains down from solution. So it's a precipitation reaction, and it makes a precipitate. And next we're going to talk about how we express these and the various ways that we express them. So there's three main ways, three different forms of equations that we can use to talk about precipitation reactions and to express them. And the first is what is called the molecular equation. And it's kind of like what you think of when you think of a chemical equation. So here is the molecular equation for the very reaction that we looked at, the pretty chemistry, the clear plus clear makes yellow. So we have the chemical formula for each. We show them that they are aqueous, they're dissolved in water, and that yields lead iodide. Notice the change from aqueous to solid. Aqueous to solid. So this is our precipitate here. And then here we have potassium nitrate. which is still soluble in water. If you check your solubility chart, you'll agree. So we put AQ there. Now, if you look very closely, you'll notice this is a double displacement reaction, a switching of dance partners. I came, here's me, with Liam Neeson, but I left in a very school-appropriate way with, I came with Justin Bieber and I left with Liam Neeson. So we have outside partners joining with inside partners. So switching those, that can sometimes help us with writing these. So the problem with the molecular equation is that it's a little bit misleading. First of all, we're treating these as if they were molecules. We even call it a molecular equation. However, we know that the word molecule doesn't even really work for salts, but also it implies some things that aren't really true. This lead isn't really with the nitrate. This potassium isn't really with the iodine. And over here, Liam Neeson and Kate aren't actually necessarily dancing. They're still spread out in the water. And so another way to express that is called a complete ionic equation. So it's essentially those dissociation equations we've been talking about, where we show them as they accurately are in the water. So here is the complete ionic equation for our yellow, beautiful, pretty chemistry reaction. So take a look at that really quick. You'll notice it's quite a bit bigger. It's got a lot there going on. So it's essentially that dissociation equation of lead and nitrate. And then the dissociation equation, it is balanced. So we want to properly reflect a balanced chemical equation every time we can. But it's more realistic because this is how they really are. The potassium and the nitrate aren't together. They're still dissolved and apart in water. And then we have here our lead iodide that we did put together because it has formed the elaborate solid crystal lattice structure. And it isn't dancing with the water and outspread. It isn't dissociated anymore, and so we put it together. So what you might notice, though, is we've got some kind of repeats on both sides of the equation. We have nitrate the same exact on both sides, and we have potassium the same exact on both sides. So these are called spectator ions because they spectate, they're just watching. These are your wingman, and if I got to meet Liam Neeson in real life, and I am telling you the story of meeting Liam Neeson, I am not going to tell you about all of the other people that are there. So we can get rid of the spectator ions who technically are there, but they actually don't participate in the chemistry of the precipitate forming. They just helped bring those ions together, but they didn't actually play a part in the chemistry happening. So that leads us then to the net ionic equation. And the net ionic equation is essentially just like the other one, except getting rid of those spectator ions. It's just the story of how the precipitate was formed. So the precipitate was formed by lead ions in water, dissolved in water, reacting in a 1:2 ratio with iodide ions, leading to this new solid precipitate, lead iodide. So let's do some practice. Predict whether a precipitate will form when each of the following pairs of water solutions are mixed. So this is where thinking about it as a double displacement reaction can be really helpful. Outside partners, inside partners.